organizers for inviting me to this exciting conference. And so what I'm going to talk today are basically two things. In the first part, I'm going to talk about several recent work on analog quantum simulation with superconducting qubits, especially related to cavity or circuit QED. And the discussion in the first part actually stimulated what I'm going to focus on mainly today, which is universal approach to quantum adiabaticity with a CQED setup. So let me start from the first part, the analog quantum simulation with superconducting qubits and CQED. And as you heard from the previous talk and also several other talks later in this conference, so there has been lots of enormous progress in superconducting quantum device. So there are two types of building blocks in this device. First, you have superconducting qubits, which can be used to emulate quantum spins, and also in 1D system, you can use to emulate fermions. We also have a superconducting resonator, which basically is microwave photon mode that can be used to emulate bosonic modes, such as phonons. And when you couple superconducting qubits and cavity together, there are many interesting many-body models you can study. So we start from the simplest models. First, we only have superconducting qubits, not the cavity. If you connect a chain of the superconducting qubit together, we will generate a number of interesting models. For example, the transverse field Ising model. So in this case, you can connect, for example, superconducting transmon qubits, superconducting flux qubits together. So this is a picture of two superconducting flux qubits coupled together with mutual inductance. And so recently, we also studied connecting a chain of superconducting qubits together and into basically a SSH model. And we use this model to study topological effects. And also we showed in this system, we can have topologically protected quantum state transfer for both a single qubit and two qubit states. So basically, if you look at this picture, we have superconducting qubits connected in different unit cell. So in this simple Hamiltonian I showed here, so this is you have two qubits in one unit cell, and then you can also connect, for example, three qubits in one unit cell, and etc. So here we showed that you can basically transfer your quantum states via the edge states. So which are basically well separated from the box states, protected by the energy gap. And we also showed that this model is actually robust against disorders in the parameter. For example, this is a calculation of the energy bands in the presence of disorders in the system. We can show that the energy gap actually is robust at basically fairly large size of the disorder. And also, now you can introduce the cavity. So everyone here is probably familiar with the Hamiltonian. So this is the cavity QED of basically an atom or a cavity coupled, or a qubit coupled to a cavity mode. So this is probably most commonly used Hamiltonian, the James Cummings model. So you have the qubit and the resonator coupled together with this Hamiltonian. Of course, nowadays, when you make the coupling much stronger, you can have the ultra-strong regime. In this case, you use the quantum Rabi model to describe the system. There are many interesting effects have been discovered in circuit QED system in the past 15 years also. So it turned out if you connect your superconducting qubit and resonators together, you can have very interesting effect. For example, in those several works, we studied an alternatively connected chain of superconducting qubits and the resonators. So in this case, the system is basically described by this coupling Hamiltonian. So each of the superconducting qubits are connected to resonators, one to the left and one to the right. And the computation between the coupling constant GL and GR basically generates quantum phase transition between the multi-insulating phase and the superfluid phase. We calculated the phase diagram of the system with a DMRG approach, and basically by characterizing the Latinger parameters in the system, we can basically derive exactly where the critical point is. So also, this is another configuration of coupled superconducting qubit and resonators. In this case, we also have one qubit connected to one cavity mode, different from the previous model. So here, what I showed here is the qubits are actually connected to each other. So this is like sort of like the SSH model configuration I showed you previously, but which each of the qubit actually coupled to a cavity mode. So in this case, we can study electron-phonon coupling in the system. In particular, we studied the small polarion formation problem in the system, also including both the Hohenstein model and SSH model. So, so now we talk about, so instead of coupling one single qubit with a cavity, so in this case, we coupled a whole bunch of qubits, or maybe more complicated many-body system, to one common cavity. So this is like doing cavity QED for a many-body system. So we start from the simplest model, which is a chain of superconducting qubits that forms a transverse field Ising model. And this model coupled to the superconducting cavity. In this case, we studied a stationary effect, which actually shows a bistable regime with bifurcation points as indicated by this figure. So here we have two control parameters. One is the driving amplitude on the cavity, the other is the detuning of the cavity, and we calculate the cavity displacement and in the stationary state, so which basically shows the bistability in the system. And also we studied the transition in the system goes through the bifurcation points. Basically, we look at the dynamics of the switching, and we showed that this can be basically explained by the Cable-Zurich mechanism. And so the study here actually stimulated what I'm going to tell you in the second part, which I'm going to start now. So this is basically about controlling, or you can say enhancing, quantum adiabaticity with the cavity or circuit QED approach. So let me first start with briefly go over adiabatic quantum computing. So this is probably a commonly used Hamiltonian of adiabatic quantum computing scheme. So at time t equal to 0, you start from an initial Hamiltonian, H0. So this Hamiltonian has a known ground state, which can be easily prepared experimentally. And then as time goes by, you slowly decrease the contribution of the H0 term in your Hamiltonian, and you slowly increase the contribution of a final term, Ht, in your Hamiltonian. And Ht is your final Hamiltonian that actually encode the target solution in its ground state. So here, Zt is a continuous function that are basically changed slowly. For example, it can be equal to t divided by the final time t. So, so this is a simple demonstration with just a quantum two-level system. You have your energy spectrum of the two-level system. If you slowly sweep your transverse field in the system, you basically go slowly from one side to the other, going through the adiabatic process. And in the whole process, the system stayed in the instantaneous ground state. There are actually lots of discussion of adiabatic quantum computing in recent years. And so there has been lots of insights in using basically this approach for adiabatic optimization problems. So to implement such scheme successfully, the system needs to basically stay adiabatic. So a commonly used form of the adiabatic criterion is basically described by this equation. So basically in this case, the adiabaticity is restricted by the energy gap in the system. However, we know that in interacting many-body systems, the energy gap can actually decrease very quickly. For example, in the Grover's search problem, in this case, the gap actually decreases exponentially with the number of qubits. And So in this case, when the adiabaticity is violated, the system can make diabatic transitions to the excited state. In this case, you cannot reach the desired ground state that you want to basically by the end of the evolution. So for quantum two-level system, the diabatic transition probability is described by the Landau-Zener formula. So it's basically exponential dependence on the gap and also the ramping rate in the system, which is basically lambda c, just the lambda here in this Hamiltonian. So in many body systems, the generation of defect goes through the critical point has been studied with the Kibble-Zurich mechanism and scaling laws. So it basically shows that you need a finite energy gap or long ramping time to have a successful implementation of the adiabatic program. So there has been lots of discussions in basically improving quantum adiabaticity with different approaches. For example, there are discussions with time-dependent ramping scheme. Basically, in this case, once you know your energy spectrum, you know your local energy separation between the ground and the excited states, you actually adjust your ramping rate to be slower in the regime when the energy separation becomes narrower. So in this case, you can basically optimize your algorithm to have better adiabaticity in the system. So there are also approaches that aim to have finite energy gap all through the evolution by choosing different evolution paths. And most recently, there's also discussion on adiabatic shortcut approach and also use the counter-diabatic interactions to cancel the diabatic transitions to the excited states so that the system stays in the quantum ground state all the time. So there's also discussions with geometric approach. So all those methods either require knowledge of the energy spectrum or instruction of some unphysical Hamiltonians. So here, what I want to show you is I want to show you a practical method that can be implemented in realistic systems. So for basically improving the quantum adiabaticity. So the scheme is I have my adiabatic quantum computer coupled to an Ancilla cavity, and the cavity behaves like a control of the adiabatic quantum computer. But different than previous time-dependent ramping schemes, here, instead of use human to control the ramping rate, which need the spectral knowledge, here I basically use a self-governed dynamics of the cavity-coupled system to basically adjust the adiabaticity. So this method is a universal approach because it only depends on some generic properties of adiabatic quantum computers. It's also a practical approach, basically can be realized in real physical systems. And in the end of this discussion, I'm going to show you the implementation of this method in 3 problems, a 2-level system, an exact cover problem, which is NP-complete problem, and also transverse field Ising model. So, okay, let's start from describing the system a little bit. So now I have my adiabatic quantum computer. It's a Hamiltonian HS with 2 terms, H0, which is the initial Hamiltonian that I discussed before, and HT is your target Hamiltonian. So different than previous schemes, here the parameters Bx and G0, they are fixed. So they are not changed. So the change of the system parameter is actually through the coupling between the adiabatic quantum computer to the cavity mode. So here I have the cavity Hamiltonian, which is a driven cavity and also dissipative, and it can be treated semi-classically. The coupling between the cavity and the adiabatic quantum computer is described by this Hamiltonian. So I have the cavity displacement coupled to H0, and given the forms of the Hamiltonian H0 in the adiabatic quantum computer, this type of coupling is usually easy to realize in real systems. So with the semi-classical cavity, we use the mean field approximation. By doing this, we actually separate the Hamiltonian into 2 terms. So the first term is an effective Hamiltonian for the adiabatic quantum computer with an effective transverse field. And the transverse field now has 2 terms. The initial transverse field, Bx, modified by a contribution from the cavity through the coupling and the cavity displacement. And the second term in the Hamiltonian is for the cavity. Now for the cavity, the driving amplitude is modified by a term related with the operator average of the Hamiltonian H0. So it's modified by the property of the adiabatic quantum computer. So basically, right now you can see the Hamiltonian actually have two separate Hamiltonians for the two part of the system, but they mutually depend on each other because the parameters depend on each other. So, and this system can be solved self-consistently. And for the cavity, we basically just use the Heisenberg-Langevin equation to describe the cavity dynamics because it's a semi-classical system. And for the adiabatic quantum computer, we use basically this Schrodinger equation with the effective Hamiltonian, which I just described to you before. And we can basically solve the stationary state and dynamical properties in the system. So, so why this is useful for adiabatic quantum computing? So let me first tell you about one generic property of adiabatic quantum computers. I think people didn't notice this before. So this is my coupling operator between the cavity and the adiabatic quantum computer. I look at the cavity average, and if I look at the cavity average in the ground state, I define this as XSS. And this is the derivative of this ground state average. I can find that this derivative is going to be expressed by this equation, which depends on the eigenstates of the Hamiltonian HS Bx tilde. So basically, the effective Hamiltonian of the adiabatic quantum computer at the effective field Bx tilde. So I can basically find a number of interesting properties from this equation. For example, the derivative XSS prime at the effective field Bx tilde much larger than the G0 term, this guy is basically approaching 0. And meanwhile, if you have basically Bx tilde equal to 0, you have a finite value. So this is actually demonstrated by this figure here, which is for the transverse field Ising model for 120 qubits. So in this case, we can calculate the derivative x prime. So we can basically show these properties indicated here from the analysis we have. And meanwhile, one interesting property is, so the derivative actually reaches maximal in the region near the energy gap because the energy separation near the gap region becomes very small due to the property of the system. And so also, the operator average in the ground state actually increases monotonically with the transverse field. And so as shown here. So with this property, I'm going to show you that we can design the system to have the quantum dynamics become very slow near the gap region. So now let's first look at the stationary state solution of the system. So with the master equation, with the equations we showed, I can basically derive the stationary state cavity displacement, also the stationary state operator average. And so this is the cavity displacement as a function of the driving amplitude epsilon and the detuning delta. There's basically the bistable region with bifurcation points in the system. And correspondingly, this is the operator average for the coupling operator. Basically, this is the property of the spins. So starting from here, let's look at more carefully. This is we get a cross section in the previous figure, but with fixed detuning with varying driving amplitude. In this case, you clearly see the nonlinear feature in the system with the bistable region, two stable solution, one unstable solution, and you have bistable the bifurcation points here. The property of the bifurcation points, if you rotate this figure by 90 degrees, so you rotate this way, you're going to see at the bifurcation points d epsilon, dxss, the displacement of the cavity is equal to 0, which means the following relation basically means the derivative of the operator average is going to be equal to alpha divided by g squared. Alpha is just a constant, depends on the detuning and the cavity damping. So basically, in this case, I showed the bifurcation point to satisfy this condition. So what we are going to do is we want to choose the parameter in this system to position the energy gap between the bifurcation points. And why? So the reason is the following. So if you look at small fluctuations close to the bifurcation points, you can write down their equations of motion. And this is the equation of motion of the small fluctuations. you can find that, so those equations have two circular frequencies. And one of the circular frequency, omega plus, have the real part actually goes to 0 at the bifurcation points. So what this indicated is the time evolution close to the bifurcation points is going to be very, very slow. So as we know that in any in any adiabatic quantum computing scheme or any adiabatic processes, the gap region is the most vulnerable to diabatic transitions because here the energy separation is the smallest. And in this case, if we place the gap region between the bifurcation points, so when the system makes transition between one region to the other, it needs to go through the bifurcation points. As a result, the gap region's dynamics become very slow, and then we basically improve the adiabaticity in the system. So what I want to mention here is, by this, we don't need to know the energy spectrum, and we don't need novel physical novel interactions in the system. What only we need to know is we need to know the operator average and its derivative at the limiting cases, basically when the starting point and end points, which can be derived analytically by perturbation theory. So now let's look at how to derive these parameters and what the requirement there is. So first, to have the bifurcation points, you need to have the detuning smaller than 0, which is easy to adjust. And you also need to have basically your parameter alpha divided by g squared to satisfy this relation, because we can derive x prime at 0 analytically, and we can estimate what the maximal is. We can find parameters to satisfy this relation as well. Meanwhile, to have the system make transition from one branch, one side of the gap to the other side of the gap, we need to have the driving amplitude satisfy this condition, and which can also be satisfied by choosing a system parameter to meet this criterion. And finally, you need to select the proper cavity damping and detuning based on the real system you have. What would be the system parameter that is realistic? And with this, we can basically study the time dependence in the system. So basically, we choose the following protocol, and meanwhile, we choose the driving amplitude as a control parameter for the system. We don't have to choose the driving amplitude. It can be some other parameters to control the system, but we use this in the following discussion. So the protocol is like this. So at t smaller than 0, the system is the initial state with a cavity displacement equal to 0. And then at time t equal to 0, we basically turn on the driving to an intermediate value, epsilon, and let the system start evolve. So once the system evolves, it's going to evolve towards the stationary state of the new, of the new driving amplitude. And then there are two cases. If you look at this figure again, so if your driving amplitude is well below the bifurcation point epsilon 2 here, the system is going to basically stay above the energy gap all the time. It's not going to cross the gap, so which is not what we want. However, if your driving amplitude basically above epsilon 2 is going to basically evolve to the other side of the phase diagram. As a result, there's going to be transition across the gap. So this is what we want. So now let me show you how this system actually works for specific examples. But bear in mind, so this is the Hamiltonian of the adiabatic computer. During the evolution, you have an effective transverse field that is modulated by the cavity displacement as expressed in those equations. So first example is a quantum two-level system. I think I'm going to skip the details of the discussion here and quickly go to the discussion of the exact cover problem, because we basically have the same conclusion for the different models. So let me go to the exact cover problem. So as we know, this is an NP complete problem. It's a subset of the satisfiability problem. So you have basically a number of clauses in the problem which you need to satisfy. Each clause actually involves 3 qubits. We can write down a quantum Hamiltonian for the system. So I randomly generate an instance for the exact cover model, so which basically is described by these 5 clauses on a 6-qubit system. You can show that these clauses actually have one unique solution that satisfies all the clauses. The solution is 1, 0, 0, 0, 1 with the first and the 6th qubit equal to 1, all the other qubit equal to 0. So starting from basically the Hamiltonian, so the Hamiltonian of this is HT. So we study basically an adiabatic evolution of the system. So initially, the effective field is Bx. So Bx tilde is equal to Bx. And then with the cavity dynamics, you change the Bx tilde to 0 slowly. By the way, this is the energy spectrum of the system as a function of Bx tilde. So in this case, this is the properties of the operator averagence derivative. It is satisfy basically the results we discussed for basically, so there's the finite amplitude, finite value for this region, and there's going to 0 in this region, and it reaches maximal close to the gap region. So, and we look at the time evolution of the system. We see something very interesting. So when your driving amplitude is above certain value, everything is above the gap region. It's not going to cross the gap. And when epsilon, when the driving is above the critical value, epsilon c, it's going to basically cross the gap region, eventually evolve towards the final value, Bx tilde equal to 0. But in the middle, when you are very close to this driving amplitude epsilon c, you are going to have very slow dynamics in the gap region, which is what we are interested in. So now we introduce a ramping rate. So lambda c is basically dBx tilde dt. So basically the change, the variation of the effective field at the gap region. In this case, we use this to characterize the adiabaticity of the system. And this is the numerical calculation we found. So the blue line is basically from the numerical calculation of the exact cover problem coupled to a cavity. And we see that when the epsilon actually goes close to epsilon c, this guy decreases quickly. And the red curve is for the linear ramping, basically between the same change of the magnitude of your effective field and the same time duration. You can see basically our method actually demonstrated strongly enhanced adiabaticity comparing with the linear ramping scheme. And so we also applied this to a transverse field Ising model. So I'm not going to talk about detail of this. I want to say that we demonstrated very similar effect as well in terms of the time evolution of the effective transverse field, and also in the ramping rate lambda, you can see there's similar behavior as what I showed you before. So then there's a summary of all these 3 models I showed to you. They all demonstrated very similar behavior, basically strongly enhanced quantum adiabaticity. What I want to mention here is, as you know, the generation of defects here depends on the ramping rate exponentially. So a few times of improvement in the ramping rate, which is shown here, which means a lot of suppression in the defect creation in the system. So with this, I think I would like to conclude the talk. So I have discussed to you about basically analog quantum simulation work we did on superconducting systems. It can be used to study a lot of interesting many-body questions, including spin models, topological effects, electron-phonon couplings, and correlated photons, and so on. And then we discussed a universal approach to quantum adiabaticity with the cavity or circuit QED approach. And this is a practical method, and also a generic method can be used to many adiabatic quantum processes. So one thing I want to mention here is we choose the driving amplitude as a control parameter, and also we choose dipole interaction. It doesn't have to be this way. It actually applies to a different type of couplings and different control parameters. And with this, I think this is the end of my talk. And thank you very much for your attention.